So same data set we were looking at last week, okay, where we were looking at pace and all that kind of stuff, and we talked about how to look at the strength of the relationship. Now what we're going to be looking at is the lines of fit, okay? And today we're going to do kind of like the what do you do once you have a line of fit, which feels backwards. And then tomorrow we're going to work on how do you create that line of fit. Okay, so the first and foremost, when I ask you guys to write about or to tell me the best fitting line to an equation, chances are I'm going to give you something from which you get the actual values. But the form in which you write the line is going to be y equals a plus bx. I bet that feels kind of familiar. Mm-hmm. Like when you look at that, what does that remind you of?
Mx plus b.
Y equals mx plus b, yeah? Except for, and don't really ask me why, because I don't really know the answer. But we tend to start with the y-intercept, and then we talk about that slope term in the statistics world. The other thing that stats does that, like, basic algebra doesn't do is it puts this little symbol, it's a hat, on the y. Okay. You guys remember when we calculated the mean, we had all these different x's, like individual values, and then the symbol for the mean was x with the bar over top. And the idea was that x with a bar over top was actually a summary of all the x's. The y with a hat is a summary of all the y's. And so it needs to be there. And it's one of those things that I hate giving a kid a P on a section of the test because they forgot their hat. You know what I'm saying? And that's what happens, and it feels really crummy. Okay. The other thing that we tend to do or need to do is somehow include context. So my favorite way to do that is to write the equation maybe like this, where my y value with the hat, and I just write the context straight into the equation, okay, is equal to 250 minus 10 times the pace. Now, I am not ever right now proclaiming that this is the best fitting line. This is a line Miss Meister made up to try to, when she was just trying to eyeball what's going on here. So when you look at this line, guys, how did I do? Does it look about right? Mm-hmm. Does it look at least close? Do you think we could get it slightly closer? Mm-hmm. Probably. We could probably do a little bit better, but I think it does a pretty darn good job. Okay? And so this is 250 minus 10 times the pace. And what's good about having this line is once we have a line, we can go ahead and use that line to make predictions. Okay, so if I told you my pace was 11 minutes per mile, now I can go ahead and take that pace out and put 11 in its place. So the predicted heart rate, BPM hat, would equal 250 minus 10 times 11. And then you guys are smarter than me. $140? 140 beats per minute. Cool.
So is it 250 minus this?
Minus the product. Mm-hmm.
Do we need to put the little hat over that?
Whenever you're making a prediction, you put the hat.
Okay.
Do we have a point that says my pulse was 140 when I was running 11-minute miles? No, it's a predicted value. It's a predicted point, not an actual point. And it makes the hat makes the distinction between what actually happened versus what really happened. Okay? And that's why we need it.
Okay.
How are we feeling about making predictions? What if I asked you to predict my heart rate if I'm running a 5-minute mile? 200 beats per minute. All right, you guys, I got one more we're going to do kind of on the side here, okay? There was a time when I was not training for myself, but rather doing what my coach told me to do. And when we'd have an easy run, we did this kind of like as slow as possible. Yeah. Sometimes as slow as 25-minute miles. So let's just for fun say what would happen for a 25-minute mile. So what if my pace was 25 per mile? What would my heart rate be?
Predicted it would be 0, but then you'd be dead.
Sad me. Sad me. We all... Now, how do you guys think this model is doing at predicting a 25-minute mile? It does a pretty bad job. Because, like, think about my pace right now at, like, 0.2. All of a sudden I'd have a negative pulse, right? When you, like, this, think about anything, in fact, anything slower than a 25-minute mile would end up being negative. So what's the problem here? Well, we kind of have, when we look at the data set that we have, the paces that we have right now are from like 8.25 to 12-ish, right? Is everybody with me? And our model is going to do a great job predicting kind of in those ranges for the paces. Does that make sense? When we start thinking about that 25-minute mile, guys, 25 minutes, I can do this, right? 25 minutes, if I extend the axis, would be like here. That's way far away from our data values, okay? So a model is only as good as the data it's coming from. Does that kind of make sense? All right, so when we interpolate, interpolation's this fancy word, and that first question we did, the 11-minute mile, we interpolated, we predicted within our explanatory variable. And I'm going to say within our explanatory data. Inside. 11-minute mile, guys, that was this point. And the reason we got 140 is because the line goes through the point 11, 140. Like, that's all the same thing. Does this make sense? Okay. Whereas, like, that 25, that's predicting outside our explanatory. And it's a bad idea. So this model would probably do a decent job predicting a 13-minute mile or a 7:45-minute mile because they're kind of close. But the further we get away from our actual values, the worse our predictions get. Does this kind of make sense? A little bit? All right, let's turn the page. All right, residuals. All right, so can you guys make the prediction for a pulse rate of 9.65 minutes per mile? 153.5. What do you guys think? It turns out one of our data points is what my pulse would be at when I ran 9.65 beats per minute, or 9.65 minutes per mile. Is everybody with me? Mm-hmm. And when you look at that, my pulse was 152. So how did the model do? Pretty well. Can we be more specific than pretty well?
Approximately the same value.
What does approximately the same mean? So we could even kind of take a look. That's this point, yeah? So how does this point compare to the line? Below it is lower than the line. And the line is the prediction, yes? Okay, so from just the picture itself, we might say the model over-predicted. Why won't this work anymore? Can we be more specific than the model over-predicted? It over-predicted by 1.5 beats per minute. And how did you get 1.5?
Just subtracted 152 from 153.5.
Okay, so essentially that 1.5 is called a residual. And it's the residual for a point is the distance between that point and that predicting line. Okay, so we might look at this point and say, oh, the residual for this point is going to be a little bit larger than, say, the residual for this point, which is going to be practically 0. Is this okay? All right, and the way we calculate the residual is we do the actual minus the predicted. So in reality, the residual for that point would not have been 1.5. It would have been negative 1.5. And what that negative tells us was the fact that the prediction was bigger than the actual point. So that it was an over-prediction. So if my residual is negative, that's over-predicting. If my residual is positive, that's under-predicting. We still feeling decent with this? So if I asked you to calculate and interpret the residual when I was running a 8:30 or an 8.3 minute mile, which technically is like an 8:20-ish. Should you guys help me out with that? What do we need to do first?
Calculate the BPM.
You have to make the prediction before you can do the actual minus the predicted. Okay, so go ahead and make your prediction and then calculate your residual. How we feeling?
So on like a test or something, you would always have to say like whether it's over predicted or under predicted.
If you're asked to interpret what the value of the residual is doing,
Okay.
remember the goal of the residual is to assess how well the line did for that specific point.
Right.
So to me, it's like interpreting a z-score. We say above the mean or below the mean, not just from the mean,
Right.
because you're trying to just show kind of where is that point relative to the line. Yeah.
So does the negative not mean that you under-predicted?
Well, so keep in mind that it's negative because the actual value is lower than the predicted value.
Okay.
So the negative, like it's kind of backwards of what you would expect. So kind of when I'm like writing out answer keys for this kind of thing, or I'm trying to interpret a residual, like to me to know that the residual will be negative when we're below the line, right? Like I actually just kind of picture it in my head. That means it's underneath the predictor.
Okay.
Think of it as the negatives describing where the actual value is, not the prediction. Everybody good? All right, now, just as a little sidebar real quick, that's not what I want to do at all. I'm going to draw a little side scatter plot here for a second, okay? Would any of you be surprised if I told you that the R for this scatter plot is 0.95? Does that look like there's a strong positive relationship there?
Mm-hmm.
Sure. Is it linear? Is a line of best fit the best fitting model?
No.
Even though R is 0.95. And R is the measure of the best linear relationship. Also, if I had drawn this at a different scale, could I have convinced some of you that this was linear?
Yeah.
I definitely could have. Okay. So one of the graphs we can do is this is a new kind of graph for most of you. It's called a residual plot. Okay? And what I'm going to do is sketch in a line of fit. This red line right here. Does that look like it's close to the best fitting line?
Yes.
Okay. Now, what can you tell me? So a residual plot goes like this. It has the x-axis is going to stay the same, and the y-axis is now the residuals instead of the y-coordinates. Okay, so in this case, so think of it as I still would have maybe pace across the x-axis, but then instead of heart rate, I just have the residual heart rates. Okay, so tell me, what do we know about the residual for this point? Is it positive or negative? Positive because it's above the line, right? By a big amount, small amount, large amount. So I'm going to make a residual that's very positive for that point. What about the next one? And the next one?
Almost the same.
The next one? Negative. And negative. And negative. Those ones look to be about the same. Barely positive and a little positive. Do we see that curved pattern on this plot?
Mm-hmm.
The curves. So a residual plot will magnify if there's a pattern outside of the line. Okay. So what would the residual plot look like if it was a good fit? What would you say?
There wouldn't be much of a curve.
There wouldn't be much of a curve. What would we see?
50% positive, 50%.
Nah, it'd be close.
Or near.
It would be close. I wouldn't say for sure you would have the same number of points above and below. But it would be close. The total sum for the best fitting line would have a residual, the sum of those residuals would be 0. But I more care about like the general form of what we might see. So did you guys say that this might be a decent fit, that this felt to you guys like it was a good fit?
Mm-hmm.
Okay, if you turn the page, look at this one over here. I would call this an exponential model the way it's written. So instead of doing linear, coming up with a line, you would try to find exponential instead. So you might have y hat equals a times b to the x, something like that. That being said, that's outside the scope of this course. Kind of. When we talk about on Thursday, where you see our topic on Thursday is going to be called straightening data. When we do the straightening of data, that's when you'll kind of see what we do otherwise. But frankly, you're going to be asked about linear data. You're not going to be asked about curved data that often. Is this okay? How are we feeling so far? Good? All right. So if you guys look at that review I passed out, I wouldn't expect you guys to answer any of the questions on the back, but you should be able to answer questions on the front. But we have to do one tiny thing. Do you guys see? Because I asked you to interpret r squared, but I didn't tell you r squared, except for I kind of did. So looking in that box of values, did I give you r squared? I gave you r squared equals 73.3%. You with me? And knowing that r squared equals 73.3%, can we find r? How? Just take the square root of it. Okay? But you got to change it to a decimal before you do that. Otherwise, you're going to end up with a value bigger than 1 for your r, which is impossible. So I was going to give you guys the rest of the period to work through just the front page of this. You're not ready for the back page yet, but just the front page.